All right, so tonight we're going to go over two problems from section 11.2. Paired difference is the one that's covered in my lab. And we also go over this Wilcoxon test, which we use when the conditions fail, and that's not covered in my lab. Now, we'll do one of each type. These problems are pretty important, not just for the final exam and so on, but this is the test that's on your research project. And so you want to use the same approach that we're using here to work on the research project. And I just recorded 3 videos that I'll upload tonight and probably email you about tomorrow about how to save your data in StatCrunch so you can type it in and then come back to work on it later, how to do any of the calculations and graphs that you need to do for phase 3. And then finally, another quick reminder of how to do the hypothesis testing in phase 4. So those are on the way. Anyway, I know this says it's a pair difference test, but we need to be able to identify those when we take our final exam. And so what we're looking for that tells us pair difference, we have 2 sets of numerical data, same sample size. So there are 10 patients, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 patients. And most importantly is that they're paired. The weight of 209 and 196 are paired together because they're for the same person. And we didn't so much care about what that person weighed before the diet as much as we're concerned with how much weight they either lost or gained after the diet. And so the starting and ending points don't matter. It's just how much weight was gained or lost. So that allows, the pair difference test allows us to focus on that. So 2 sets of numerical data, they have to have the same sample size. If they have different sample sizes, you know it's not pair difference. And then finally, if they do have the same sample size, then you've got to make sure that they belong paired together, that they have something in common. When you would do this in StatCrunch, you would type one set in one column, and then the other set would go into the second column. But tonight, I've already got these loaded in a file in our Woodbury Math 21 group called Zoom 11.2. And so I'm going to show you how to get to that. For those of you who haven't joined the group yet, there's a video for how to join the group, and you can go back and look at that first. But if you're already in the group, after you've logged into StatCrunch, you click on My Groups, and you'll have one that says Woodbury Math 21. And then in the search bar, just type in Zoom 11.2, and there's only one file that says that. So you click on that, and the problems, the data for tonight's problems are there. The first 2 columns go with problem 1, and the second 2 columns go with problem 2. So you won't have to retype these in, but on the exam, you're going to get a problem just like this, and you've got to type them in, make sure that all that first row before goes in one column vertically. And then the second row after goes in another column vertically. All right, let me blow this back up. The first thing that you have to do when you're doing any of the tests from chapter 11 in step 1 is you have to tell me which group is going to be population number 1. And if you look at the claim, you want to see if there's a group mentioned first. And so here, claim that the diet is effective. In other words, the diet will reduce the weight of a person. It doesn't say anything about before or after. So when that happens, you can just let the first set of data be population 1. So I'm going to let the before weights be population 1. The null hypothesis for every paired difference test is mu d equals 0. That's the mean of the differences between the 2 pairs is equal to 0, meaning if that mean is 0, then the 2 pairs are actually the same. For H1, we've got to figure out what sign belongs in there. And really the best way to do this, let me change colors for this, is if you list population 1 and population 2 and try to think about which one's supposed to be lower or higher. So here it's talking about reducing the weight, and automatically we think about that as being getting smaller. We think about a less than sign, but actually what that means is that a person's weight after will be lower than their weight before, or their weight before will be the higher weight. And so the sign that we need to use is actually the greater than one here. And probably the trickiest part about the pair difference test is coming up with the right sign for H1. If you have the wrong sign, you'll get one more chance to bail yourself out when you get to the part where you do the calculations. If you see a gigantic p-value, 0.7, 0.8, 0.9, then there's a good chance that you've got something backwards, and you definitely want to go back and check to make sure you've got everything in the right order. Right. Back to this hypothesis test. Second step, pretty straightforward. Level of significance is 0.01. Third step, it looks like it's pair difference. And I say that because there are conditions that we have to check, and we won't really know until we try to do it as a pair difference whether those conditions are good or not. And there's two things that we're looking for. We want our Shapiro-Wilk p-value to be above 0.05. And we're also looking for no outliers on the box plot. And StatCrunch will calculate those for us as we go through the process of doing the pair difference test. The StatCrunch steps for that are stat, t-stats, and paired. So I'm going to split the screen again, and we'll walk through the calculations in StatCrunch. Stat, t-stats, paired. Sample 1, I have to use before for that, so before. Sample 2 will be the other one after. The difference is we don't really need when we're doing any of these Canvas problems, but when you're doing your research project or you're doing any of the MyLab problems, you probably want to save the differences because you may be asked to do some calculations with them. For the null hypothesis, never change that value of 0 in chapter 11. So this week, 11.2, next week, 11.1 or 11.3, we don't change that at all. But for HA, we need to bring over the sign still from our H1, which was greater than. And finally, to check the conditions, if you scroll way to the bottom, highlight from box plot down to Shapiro-Wilk, just like we did for the one mean test. The box plot will tell us if there are any outliers. Shapiro-Wilk is how we figure out whether the data are normally distributed or not. The compute. And the first thing, right, we're tempted to look at the calculations, but we have to check the conditions first. And down here, the Shapiro-Wilk p-value is 0.5475. Oops. And that is above 0.05. So that one is good. And by the way, we always use 0.05 for that, no matter what the level of significance in the problem is. We're always testing that at 0.05. So that never changes. To see the box plot, click on the right arrow. No outliers there. And so this meets the conditions for a pair difference test. Now, if those either one or both of those conditions fail, then we've got some editing to do. We need to change our HO and H1 in terms of the symbols. We change the name, and then we have to recalculate. But because the conditions were good, we can take our test statistic and p-value right out of the problem. The test statistic T is 3.01 rounded to 2 places. That means basically that the before weights are about 3 standard deviations higher than we expected them to be if there was no difference. The p-value is pretty small, 0.0074. If we repeated this experiment 1,000 times, we would expect to see results like this maybe 7 times. And that's unusual. This is a low p-value. If you compare the p-value back to the level of significance, 0.0074 is below 0.01. Once we get to that point, then we go back to everything we learned last week and the week before that. A low p-value means that we reject HO. And when we reject HO, that means that there is sufficient evidence to support that. And here, we want to take a look at the sign in H1. If H1 is a less than sign or a greater than sign, that means that we can take the wording right out of the problem. If H1 is a not equal to sign, then we need to rewrite this in terms of being different. But because the sign was greater than, we can take it right out of the problem that this diet is effective. And you can add the other part too if you want to. The diet will reduce the weight of a person. The low p-value means we have strong evidence and we were able to show that this diet actually works. If we had a higher p-value, it doesn't mean that the diet doesn't work. It just means that we can't show that it works. So low p-value, strong conclusion and decision. Weak p-value, weak conclusion and decision. All right, before we move on to the second and last problem tonight, I'll give you a minute. If you have any questions about any parts of this, you can type them into the chat or you can unmute yourself if you want. And then we'll go on to the second one. So the second problem is an example that you need to use what's called the Wilcoxon test. And again, when you're taking the final exam, they're not going to be labeled like that. And so we've got to be able to spot them. And first, that means spotting that this looks like a pair difference test. And so just like the last problem, we have 2 sets of numerical data. That's the first requirement. Both have n equal to the same number, right? There's 13 fathers, there's 13 sons. So that's good. And then what we know is that this father and this son are tied together because they're in the same family. So we're trying to see how far off from the father the son is. It doesn't matter how tall the father is, it's just how far off the son is. So they are paired. And that means that this starts as a paired difference problem. So I'm going to blindly, even though it says Wilcoxon up at the top, I'm going to blindly go through this as if I didn't know that. And then I'm going to run into a problem when I check the conditions. And I'm going to show you how to adjust to that and come back and straighten out the parts that were different. So step 1 again, you've got to list population number 1. And this time the claim mentions the 2 groups. If we look at the claim, that's the claim that sons are taller than their fathers. And so it mentions sons first, and this is the most dangerous one. Because if we use sons as group 1, notice that the data for fathers shows up first and sons shows up second. There's a real good chance to get those backwards from each other. And we definitely want to be careful of that. So if we let population 1 be the sons, The null hypothesis, again, is mu D equals 0. And for H1, I need to figure out what sign goes in there. And so again, if I list sons first and fathers second, it says sons are taller than their fathers. That means to use the greater than sign. And we use the same thing in H1. Now, in a moment when these conditions fail, I'm going to have to come back and change what I wrote here, but I'll edit that in a sec. Step 2, level of significance this time is just 0.05. That won't change. Step 3, the name of the test is pair difference. That will change as well. When the conditions fail, it's got a different name. It's called the Wilcoxon test, and we'll come back and fix that in a minute. A quick reminder of the conditions. We need Shapiro-Wilk p-value above 0.05, and we need no outliers on the box plot. And if one of those works, but one of them fails, that's a fail. You just need one of them to fail to have to switch the test. So again, at this point, we think it's pair difference, and we check the conditions by doing the pair difference test. Now, sometimes that means that we've done a little extra work that we have to throw away, but that's the way, the most efficient way to do this. Stat T paired. Sample 1, remember, was sons, not the fathers. And sample 2 is the fathers. Different than the order they were listed. HO, mu D equals 0, we don't change that. HA, we need to use greater than. And again, from box plot through Shapiro-Wilk. Compute. And on the first page, Shapiro-Wilk is okay. We've got 0.5309, and that's above 0.05, so that one is good. We go to the next page, however, there's an outlier. It says in row 9, that son was 7.9 inches taller than their father, and that was an outlier here. So there is an outlier. That condition fails. And so what that tells us, let me change the orientation here, put this up a little bit, is when we go back to HO, it's now going to be MD equals 0, M for median. Just like we did for the sign test. And that means for H1, it's going to be MD is greater than 0. Also for step 3, now we're going to call this Wilcoxon. And so we're going to have to recalculate the Wilcoxon test is under stat, non-parametrics, Wilcoxon. But before I do that, I do want to come back to StatCrunch real briefly. I'm going to show you what you would see if you picked the data in the order they were typed. So if you pick the father data first and the son data second and hit compute, notice the p-value here, really big, 0.6939. That is a sign that maybe you've got something backwards. So notice I've got father listed here first, but in the claim, it says sons are taller or greater than their fathers. And so sons either needs to be first, or you can't use the greater than sign. One or the other has to go. And so if you get a big p-value here, that's really your last chance to recognize that. All right, back to the problem that we were on. The calculations, stat, non-parametrics, Wilcoxon. Click on paired, because this is a paired test. Sample 1, again, is under son. Sample 2 is under father. For HO, don't change the 0, but change HA to match the sign we picked. Like that. And notice right in here, it says median, right? It's changed from mean. Click compute. Might fit on the screen. There's our results. And the number we want is the p-value, 0.3633. So we take that back to our problem. Step 4, p-value equals 0.3633. And when we compare that back to the level of significance, this is a high p-value. So to finish this off, step 5, high p-value means fail to reject HO. And that means there is not sufficient evidence to support that. And here, this is where either the claim goes, or we need to reword the claim in terms of being different. If you look at the sign in H1, greater than means that we can use the wording that was in the problem. And so when we look, it says sons are taller than their fathers. You can copy that down. Sons are taller than their father. Now, one place, one thing that we saw in the sign test is that we had to change the word mean in the claim to median. However, for paired difference, we rarely see the word mean in the claim. So there was nothing to change here. Now, another thing that's really important, the last part of this problem, I spent writing this, sons are taller than their fathers. And so in my mind, I may have this idea that I just showed that sons are taller than their fathers, but I actually didn't, because I couldn't reject the fact that they were the same, and I did not have enough evidence to show this. So when you have that high p-value, even though I just wrote sons are taller than their fathers, the beginning of that sentence matters, that I couldn't show that sons are taller than their fathers. Now, that, again, doesn't mean that sons are shorter than their fathers. It's just that I couldn't prove that they're taller than their fathers. And so you want to be really careful with those conclusions, because on the final exam, you're going to be asked to interpret that. And so it'll be a multiple choice question. You'll be asked, I proved that I showed that sons are taller than their fathers. I couldn't show that sons are taller than their fathers. I showed that sons are shorter than their fathers. You'll be given options like that, and you've got to figure out which one is the right one. When you reject HO, you've showed that H1 is true. And when you fail to reject HO, you're unable to show H1 is true, but you're not showing H1 is false either. It's kind of like our jury system. If you're on trial and there's not enough evidence, you're found not guilty. You're not found innocent, you're found not guilty. And that means we didn't have enough evidence to prove that you did it, but it doesn't mean that we're saying you didn't do it. We're not proving that that negative, we're just unable to prove the positive. All right, any questions on this one? Again, the Wilcoxon test, not covered in my lab. So the only place that you have access to these materials are through my notes in Canvas for this week's module and in the video that I recorded for that. There's another summary video where I work through a couple of problems of these types, kind of like we did tonight. So between tonight's Zoom and that summary, that's a really good wrap up of this section. All right, let me stop the recording.